Now let's see how to represent the fractions in or the binary number with radix point, which is a floating point number, into computer. So now we have seen the conversion. Now let's talk about the representation. Okay, so let us say we have a floating point number like this. See, what is the main difference between floating point and fixed point number is, in floating point number the radix point can be anywhere. For example, if I have a number 4.5, this is a floating point number because the radix point here, which is also called as decimal point in decimal number system, is in between these two numbers, right? In case if you move it either to the leftmost or to the rightmost, then that is called as fixed point number, right? Now we have seen how to convert a floating point number into binary. Given that it is in decimal, how to convert it into binary. Now what I want to see is how to represent this number in the computer. That is what I wanted. Why? Because we want to store such numbers in computer and then we want to manipulate them. So I want to convert them into binary and then save them in the computer in such a form that I'll be able to again convert them back and do some operations on it. Okay, so whatever representation you are going to use should be easy for us to convert it first, and second thing is it should be easy for us to apply some operations on them. You have to keep those two in mind. Now what is the value of this? Value of this one is going to be 1 0 0, it is going to be 4, and then 1 is going to be 5.5, right? So how to store it in a computer is, so earlier people used to follow various conventions. Some people used to follow saying that represent the entire binary number as it is 0 0 0, let's say, and then see count where the floating point is, and you can write where the floating point is, right? So like let's say the floating point is after 3 bits, right? But then this one was found to be very inefficient. So later people have used something like this. So they have dedicated one field for the sign of this number, and then they have dedicated one field for the mantissa, and then they have dedicated one field for the exponent. So what they try to do is, in order to save this number, they try to move this decimal point to the to the front of this one, and then they try to apply this way. So in case if you represent this number as 0.1001, so since you have decreased this number by moving the radix point towards the left side, you have decreased the number by how much, and so you are increasing the number by 2 power 3. These two numbers are actually same. So however, the same way you do it in decimal, whenever you move the decimal point forward, you are actually decreasing the number, then you are going to multiply with 10 power something, right? So here also I am multiplying it with 2 power 3, right? Okay, now see, why is this conversion true? Then if you have any doubt, you can just convert it back. So what is this number going to be? This one is going to be 2 power minus 1 weight of this one, and this one 2 power minus 2, 2 power minus 3, 2 power minus 4, right? So which is nothing but 2 power minus 1 plus 2 power minus 4 is this number, right? And now if you multiply with 2 power 3, then it is going to be 2 power 2 plus 2 power minus 1, which is nothing but 4 plus 0.5. So writing like this is okay. Now what they thought is, we can save this number in the mantissa part, and we can save this number in the exponent part, and we can save the sign of this number in the sign, right? Which means for this one, if you observe it, we are going to save this sign as 0, and assuming that there are 4 bits enough to save here, so let us say 1001 can be saved here, and 3 is this. So simple representation. But there is a problem with this representation. The reason is, if you don't have any other rules, if you are directly going to use this way, then I can come up with one more representation. So one more representation is going to be 0.01001 into 2 power 4. So again I am going to get the same number for this representation. Now for this one, if you save this, it is going to be, sign is going to be 0, and mantissa is going to be this entire number, right? So 0, assuming that these many bits are available in the Mantissa field to save it. So 0 0 1, and then what about 4? 1 0 0, right? So again sign, Mantissa and exponent, right? So now if you observe it, there are many representations for the same number. That is the problem. Already I told you that with 10 bits you will be able to get only 2 power n combinations, and with these 2 power n combinations you are trying to represent infinite number of numbers. The reason is you are going to have infinite number of real numbers, even just between 0 and 1. Now you are trying to represent every real number with only 2 power n combinations, out of which if more than one number is taking away the two combinations, or one number is taking away two combinations out of 2 power n. In fact, here same number is going to take away many combinations, right? Then we will not be able to represent all the numbers efficiently. We will be able to represent only few of them. Got it? So what to do is, we should be careful in such a way that every number should take only one representation. Then only we can use these numbers efficiently. Got it? So the next rule that is applied is normalization, right? The first rule is, let's save it in terms of sign, magnitude and exponent. That is the first rule. And the second rule we are trying to apply is how to save it using, how to see that every number is going to get only one representation. For that we are going to go for something called as normalization. So what does normalization say is, don't use all the representations, just use one representation for every number. For example, if you take this number 100.1, then you move this radix point just before the first one. So wherever you see the most significant one, you just move it till there, and that is the only representation we are going to use. No other representation for that number. Therefore for this one, the correct representation is going to be 0.1001 into 2 power 3. Got it? So if you are going to move this radix point exactly before the most significant one, this is called as normalization, and even more it is called as explicit normalization, right? And now depending on the fields, you are going to save everything here. Now let us say the fields is, one is sign and other is Mantissa and other is exponent, right? Or you can also write it as sign, exponent, Mantissa. So if you write this way, I think you will remember it better. Sign, exponent, Mantissa. If you write this way, you can remember it. But anyway, what is the actual representation they have used? They will mention it in the question. Either this way or this way, they are going to mention it. Okay. So this is the standard way. SCM is the standard way. And now 0 is going to be the sign and exponent is going to be 3. So let us assume that 4 bits are given for exponent. Then how are you going to represent it? 0 0 1 1. And for Mantissa, let us say 5 bits are given. Then how are you going to represent? 1 0 0 1 0. Why? Because even if I add a 0 here, it doesn't change the value, right? So this is one representation for this number. Okay. And next thing is how to deal with the negative numbers. So sometimes you are going to get positive numbers here in the exponent, and sometimes you might get negative numbers also. For example, if I say I have a value 0.101. So this is the value I want to represent. Then how to represent it is, I want to move this one to the right of it. So whenever I move the radix point to the right, I am actually increasing the value, right? So how to decrease the value? If I am increasing the value like this, so 0.101, which means I have moved it to 2 points right, then I have to multiply with 2 power minus 2. So this is the way I decrease it. Now what is that I should represent? One thing is sign. Sign of this number is positive, which means I can use 0 to represent it. And then what about the exponent? Exponent here is minus 2, right? And Mantissa here is 101. Now whenever you see a negative number, there are various ways you can represent a negative number, right? So one is 1's complement and other one is 2's complement, and there are various other representations as well. But if you consider 2's complement, that is better, because 2's complement is the most popularly known number system to represent negative numbers, right? So let's see what happens if I represent it using 2's complement. So I'm going to represent it this way. Let us say for sine 1 bit is given, which means 0 will be given there, and for exponent 4 bits are given. Let's compute what to write there. And for mantissa 5 bits are given, therefore 1 0 1 and then 0 0 is given for mantissa, 5 bits, right? Now what about the exponent? Exponent has to be a negative number in 2's complement, which means minus 2. So if you see 2 in 1's complement, 2 in positive, it is going to be 0 0 1 0. So since we are talking about 4 bits, I am writing it as 0 0 1 0. Now convert it into 2's complement. So how to convert it? Convert it into 1's complement first and then add 1. So this is the 2's complement representation of minus 2. So we are going to write it here 1 1 1 0, right? So now how to get the number back? Once you know that you are going to use this form, then how to get the number back is 0. So minus 1 power s into, which means sine, into 0 mantissa into 2 power exponent. You can directly write it this way. If you know that this is the way you are going to store a number, then how to convert the number back into decimal? You have to use this formula, isn't it? Why? Minus 1 power s means, in this case minus 1 power 0, it is going to become positive, right? So whenever you put s equal to 1, the entire number is going to be multiplied with minus 1. Whenever you put s equal to 0, the entire number is going to be multiplied with plus 1, right? Into 0.m. So what is 0.m? 0.101 into 2 power exponent. So since you know that you have used 2's complement representation here, you can directly convert this 2's complement number, right? So this is nothing but minus 2. So you are going to get minus 2. So this is one way of storing it. Now there is a problem with this. So the representation is fine. For every number you are going to get only one representation. Now we are going to get only one representation by this normalization method. But then coming to the exponent, we are actually directly representing a negative number also into the exponent. Now later when we have two numbers and if we have to compare them, then comparing directly 2's complement number, if it is represented in negative, if a negative number is represented as it is a problem. That is why sometimes we are going to use, or always we are going to use, something called as biasing. So biasing is a method by which we can convert every negative number also to positive. So for example, if you have 5 bits, using 5 bits, how many numbers can be represented in 2's complement and what is their range? So using 5 bits, we know that we can represent minus 2 power n minus 1 to 2 power n minus 1 minus 1. So which means we can represent from minus 16 to plus 15, isn't it? Now what we do is, comparing the numbers when they are represented in this range is difficult for a comparator. So if we can convert all the numbers to positive, which means if we can write all the numbers from 0, then it will be easy. So what we do is, for this entire range we generally add plus 16 plus 16 plus 16, and even though the actual number we have to represent is a negative number, we'll convert it to either 0 or a positive number, right? See, if we have a range from 0 to 16, if I add to every number in that range a number 16, then the range is going to be from 0 to 31, isn't it? Now even though the actual exponent is something, I'm going to represent the exponent as a number which is lying from 0 to 31 by using this biasing method. So why do I do this is because comparing two numbers in this range is easy by looking at their bit representation, right, in binary, without converting it to decimal. Now comparing two numbers given in this range is difficult if they are represented in binary, especially in 2's complement. Got it? So that is why I am going to use the concept of biasing. So in the earlier case, even though I had to represent minus 2, right, for example, if this is the number which I wanted to represent, even though I had to represent this, so which means 0. Let us say 101 into 2 power minus 2, this is the number which I wanted to represent. Now even though I have to represent minus 2, I'll take minus 2 and add a bias of 16, and now I'm going to represent 14 in that. Getting this? So now what I do is, see this, so our representation is going to be, let's say 1 bit is given for sign, and then how many bits? 4 bits are given for exponent. Let us assume that 5 bits are given for exponent, and let us assume that mantissa is going to take 4 bits. Okay, now what is that we are going to represent? 0 is going to be represented in this sign, and coming to exponent I am going to use 5 bits. So using 5 bits I am going to represent 14 only, not minus 2, right? So here I am going to represent 0 1 1 1 0, right? I think that is 14. Okay, so this is going to be 14, and then the mantissa is going to be 1 0 1 0, right? So now what did I do? I have biased the exponent with 16, which means I have increased the number by 16. So what is the normal biasing that you should use? If you are going to have in the exponent n bits, then in 2's complement number system I can represent a range from minus 2 power n minus 1 to 2 power n minus 1 minus 1. Now in order to convert all these numbers to positive, you have to take the most negative number and add it as the bias. Therefore the bias in this case is going to be plus 2 power n minus 1. So this is how you can decide what is the bias you need to use, right? Or in any other number system, if you are going to go for example, if you are going to use 1's complement, then find out what is the maximum negative number you are going to get and add it, so that all the numbers are going to be from 0 to positive range. Then comparison will be easy, right? Okay, now this is what I am going to use. Now since we have changed the representation, you have to also change the conversion formula, right? So what is the conversion formula? Minus 1 power s, it is going to give you the sign of the number multiplied with 0 point, so this I didn't change it, isn't it? 0 point mantissa into 2 power. Now actually this exponent doesn't represent the actual exponent, this exponent represents the biased exponent. Therefore whatever is there in the exponent field, you take it as it is, as if it is a positive number, and from that you subtract the bias. So why should you subtract the bias? Because you have added it while storing it, then you are going to get the actual number, right? So now for this number, minus 1 power 0 into 0 point m, so what is m? 1010 into 2 power exponent. So what is the exponent here? It is 14. So 14 minus bias, which means 16, then what do I get? Minus 2. So it is going to be 0.101 into 2 power minus 2 is the number. That is what you have saved it. Got it? Okay, now this is what is called as normalization. So what are the methods that we have used? One is I have used normalization, right? And in particular this normalization is called as explicit normalization. Why explicit normalization is, okay, I'll tell you when we discuss about implicit normalization. So the method that I used is explicit normalization and also biasing. So biasing means I have added some number to the exponent to make it a positive number. Okay, so now in the next video we shall see what is implicit normalization and what are its advantages compared to explicit normalization. Okay, fine.
Hi, if you are planning to do masters, then doing masters abroad is better than doing masters in India. I'll give you all the reasons. So, first reason is, out of 1 lakh students who take GATE every year, there are only 500 seats in old IITs. So all the IITs put together have an acceptance rate of 0.5%, and IITs, universities better than IITs, they have very good acceptance rate like 30%, 40%, but all the IITs put together have an acceptance rate of 0.5%. And if you are working hard to get into IIT Bombay's ranking is 177 and IIT Roorkey's ranking is 400. If you are happy to get into IIT Roorkey, then getting into universities better than IIT Roorkey is easier compared to getting into IIT Roorkey. And looking at the salaries for computer science, for software jobs, if you have done your masters in computer science in US, the salaries are ranging from 80 lakhs per year to 1.2 crore per year. So even if you take an average of 1 crore per year, your savings will be much higher than the salaries in India. After taxes and your cost of living, you can easily save 40 to 50 lakhs per year. And in India, the maximum jobs that you get is around 30 lakhs. So your savings will be much greater than the salaries in India. And these are all the services that we provide. University shortlisting. So depending on your profile, we will shortlist what are the universities that you have to apply, and statement of purpose building, and then LOR guidance, and GRE and English test assistance, and education loan assistance. So you don't have to have any collateral, which means without any security, now you can get education loan. Getting education loan is very simple these days, and whatever the amount of fee that you have a range of universities. You can apply for 10 lakh universities, 20 lakh universities, or 50 lakh universities. But whatever it is, you are going to get complete education loan, and you can pay off your education loan in 1 year after you get a job. And then we do visa assistance, mock visa interviews, and then connecting with the university alumni. So now you might ask why we should join Game of Visas. So the answer is we have 90% success rate, 99% success rate. And these are all the destinations that we guide the students to. So we guide students to any country that you want to go. So now it is not just USA. We guide to UK, Germany, Australia, Canada. So we guide students to all the countries. We work with all the destinations. And if you are interested in going abroad, you have to just drop us a message on this WhatsApp number 9494 555 454. Okay, thank you.